Hello, welcome back to our little corner on the web, where we go over math problems to hopefully encourage and foster a love for math. Today, we will go over question 13 in part 1 of the 26th Philippine Math Olympiad area stage. Okay. Thank you to our organizers for freely sharing the questions. So question 13 says, let n be the smallest positive integer for which there are exactly 2023 solutions or positive integer solutions, xy to the equation 1 over x plus 1 over y is equal to 1 over n. Determine the first 3 digits of n. Okay, so to some of you, this might look familiar. This equation here might look familiar, that it's a form of Simon's favorite factoring trick. So we'll basically try to multiply x, y, n all of throughout the equation. Okay, so we'll get this. That's partially to get rid of the denominator and get into a form where we can start factoring it. Okay, so as you'll notice, that's just basically nx plus ny equals xy. Rearranging all the things to one side, we can start to factor it. We'll notice that we have an n squared that's missing. Why is that? If you just factor x from the first two terms, we get y minus n. So this y minus n here. So the n squared added to both sides is so that we can factor the left-hand side to x minus n, y minus n. This is basically Simon's favorite factoring trick. Okay, you guys might, some of you might just jump in and say, oh, we just need to find basically numbers that multiply to n squared and say that we just need to find 23 factors of some number n squared. Well, that's true, but we sort of want to make sure that our proof is complete as well. So we want to show that there doesn't exist a case where x is positive, x minus n is negative, right? And we're dealing with a y that's positive and y minus n is negative, because negative is positive. So we have n squared. We can potentially have n squared where both of them are, or at least one of them is positive, one of them is negative, or both of them are positive, right? So we want to exclude certain cases so that our proof is complete. So we notice that if x is between 0 and n, right, we can subtract n through this inequality and have negative n and 0 basically bounds x minus n. So that means that x minus n here in this case is negative, okay, where x is positive. Okay, if x minus n is negative, then y minus n has to also be negative, right? And not only negative, it has to be less than negative n. Okay, because if x minus n is in between negative n and 0, the only way to get n squared is if y minus n is less than negative n. But if that's true, y is less than 0. So we don't have a case where x is less than n, but positive, and y is also positive. Okay, so at least we can take that corner case out. So the only cases that's really going to be valid for x and y to be positive is x is greater than n and y is also greater than n, meaning both of these factors are actually positive. Okay, so we can just now go ahead and really figure out how many, for which n, right, the smallest n that has 2023 positive integer factors. Okay, so if you hopefully remember how to count factors, we can express the factorization of a number n, prime factorization of a number n as P1 to exponent 1, P2 to exponent 2, P3 to exponent 3, where the p's are prime numbers. Okay, this means that n squared can be expressed as P1 twice of the first exponent, P2 raised to the twice of the second exponent, and so on and so forth. What we're looking for is that the product of the exponent of the first prime plus 1, exponent of the second prime plus 1, and exponent of the third prime plus 1 is equal to 2023. And there might be more, right? This could be 2 times e sub 4 plus 1, 2 times e sub 5 plus 1, and so on and so forth. But so what we're going to do here is factor 2023. 2023 turns out to be 17 times 17 times 7. So there's only 3 terms here. The rest of the terms are 0, meaning E4 is 0, E5 is 0, and so forth. Okay. So 17 times 17 times 7 can be expressed as 2 times 8 plus 1, 2 times 8 plus 1, and another term which is 2 times 3 plus 1. That means that E1, E2, E3 is nothing more than 8, 8, and 3. Okay. So we're looking for the smallest n. So to minimize n, we're going to look for the smallest primes that we can have to express n, right? So it turns out that those will be 2, 3, and 5. So it's simply 2 to the 8 times 3 to the 8 times 5 cubed. Okay. You could have done this thing faster. You didn't need to go 32 times 729 times 1,000. You could have said 5 cubed pairs with 2 cubes. So you're only really dealing 2 to the 5th and 3 to the 8th, right? But in any case, if you multiply that out, you should find that the first 3 digits, which we're looking for in this problem, is 209. Okay. So hopefully this solution was helpful to you. If you liked it, please do hit the like button and subscribe. Thank you for watching.